So in section 5, we're going to look at graphing linear inequalities and then systems of linear inequalities. So far we've only talked about systems of equations, whether that was 2 or 3. But we can also solve a linear inequality with 2 variables. So with a system of equations, you find a single point that is the solution. But with an inequality, because you have a region of possible answers, you find a set of possible solutions. So there's more than one answer when you're solving a linear inequality. So couple things when you are graphing a linear inequality with 2 variables. So we're talking about x and y, not just x or y. So the first thing you're going to do is graph the inequality as if it was an equation, and that creates what's called the boundary line. That's the line that kind of, depending on your inequality, tells you that my solution doesn't fall on the other side of this line. Then you have to determine whether or not that boundary line will be part of the solution set. So if your inequality contains equality, so that's a less than or equal to or greater than or equal to, then the points on the line are part of the solution set. So we would use a solid line to graph that. So there's just a solid line. If it does not contain equality, so it's a strictly less than or a strictly greater than, then the points on the line are not part of the solution set, in which case we use a dashed line to indicate. After that, the final part is determining which side of our line contains our solutions. So typically we do that by picking a test point on one side, not on the line, but on either side. And the most common test point, as long as it doesn't fall on the line, is the point 0, 0. It is the easiest test point to use. So we would plug that into the inequality. If you get a true result, then the region that contains that point would be shaded. And if you get a result that's false, then the shade, you would shade the other region. So before we look at a system of linear inequalities, we're just going to look at graphing singular inequalities. So for our first example, we have x plus y is less than or equal to 2. So in order to do my boundary line, I have to get it in my y equals mx plus b form, like when we were graphing linear equations. So that means I'm going to subtract x from both sides, and we're going to end up with y is less than or equal to negative x plus 2. So the first thing I'm going to do is I'm going to plot the points for, if it were a regular line, for negative x plus 2. So my y-intercept is a positive 2, and then I have a slope of negative 1, so that means down 1 over 1. Now I have to determine whether or not I'm going to have a solid line or a dashed line. And because my inequality is less than or equal to, that means I'm going to have a solid line. I'm going to use a solid line to connect my points. My last step is to go ahead and plug in my point 0, 0 to see which side of that line I'm going to shade. So I'm going to test the point 0, 0. So y is 0. So 0 less than or equal to 0 plus 2, which leaves me with 0 is less than or equal to 2, which is a true statement. 0 is less than or equal to 2, which means I'm going to shade the region that contains the point 0, 0, which is everything below the line. So that means any point that falls, because it's an equal to, on the line or below the line, is considered a solution to this inequality. So there's a lot of different points that you could potentially do for this. So there's not just one solution. Any point that falls in our shaded region is a solution. Okay, so next we have 3x minus 4y is greater than 12. So I have to get it in my mx plus b form. So I'm going to subtract 3x. So we get negative 4y is greater than negative 3x plus 12, then we're going to divide everything by negative 4. Important thing to remember here, if I multiply or divide an inequality by a negative number, I have to remember to flip the inequality. So it's going to be y less than, and then negative 3 over negative 4 is positive 3/4 x, and then minus 3. So my y-intercept is at negative 3. My slope is now a positive 3/4. So I'm going to go up 3 over 4. I'm going to go down 3, left 4. Okay. This time I have strictly less than, which means I'm going to have a dashed line going through my points. Okay. Now I'm going to plug in my test point of 0, 0. So we get 0 is less than 0 minus 3. 0 is less than negative 3, which is not a true statement. 0 is actually greater than negative 3, which means I don't want to shade where negative 3, where 0, 0 is, which means I'm going to shade over in this area. Now, the difference between my solution, my previous solution to this one, unlike my previous example, where any point on the line was also part of the solution region, in this case, because I have a dashed line, any point on the line is not actually part of the solution. So I only can pick points that are in my shaded region to be a solution. Last example we're going to look at before we talk about systems of inequalities is if we don't have two variables. So we're going to kind of review our horizontal and our vertical lines here. So if I have y less than or equal to negative 4, this is a horizontal line. So my points only go through negative 4 because that's my y value of negative 4. So any point, so this is an example of a horizontal line. So, and it isn't equal to, so I'm going to do a solid line. This one I don't really need to use a test point because I don't have two variables. Anything that would be below negative 4 is going to be anything underneath my line. So I'm going to shade everything below negative 4. The only value you need to really test is 0. Is 0 greater than negative 4? Sorry, 0 less than or equal to negative 4? No, it's not, so I shade below the line. It would work the same way for a vertical line. So vertical lines is going to be of the form x, and then an inequality of some sort, like greater than or equal to, and then some number a. So vertical line is just x, and then an inequality. So those would be the ones that go straight up and down. Oh, forgot there was one more example. So vertical line, x greater than 5. So this is our vertical line. So this time it goes through my x value of 5, so just my points containing 5. And then because this is a strictly greater than, I'd have a dashed line. And everything greater than 5 is everything to the right. So now we're going to talk about a system of inequalities. So we saw, I had mentioned this before, when we had a system of equations, the solution was just where they intersected. But if we looked at a system of inequalities, the solution is a region, not just a point on where they intersect. So the solution to a system of linear inequalities is the region where the solutions to each inequality overlap. So you graph each inequality, you graph their solution regions independently, and then you look for the overlap. And wherever those two inequalities solution regions in overlap is the solution to your system. And then the intersection point, which we'll look at an example, the intersection point may or may not be a solution to the system. It depends on whether or not you have two solid lines or one of them is dashed. If you have two solid lines, then the intersection point is a solution. If one of the lines is dashed or both of them, then points on that line or both of those lines are not part of the solution region, which means that the intersection point would not be a solution. So one way we can check whether or not a point is a solution is to check it in our inequalities, similar to when we were looking at a system of equations. So I want to know if the point 3, 6 is a solution to the system of linear inequalities. So I'm going to plug that in for x and y in both of my inequalities. So 3 times 3 minus 6 has to be greater than or equal to 3. 3 times 3 is 9, minus 6 greater than or equal to 3. 3 greater than or equal to 3. So because I have an equal to here, I can say that that is a true statement. 3 is greater than or equal to 3. Now I'm going to check my second inequality. So x plus y, 3 plus 6, less than 11. So I get 9 is less than 11. Also a true statement. So yes, 3, 6 is a solution because both inequalities are true. So very, very similar to when we're looking at a system of equations to checking a point, I had to have a true equation in both cases. In this case, I just have to have a true inequality. So it's not like both sides have to equal. As long as the inequality is true, then it is a solution to the system. So let's look at finding the solution region by graphing. So like I said before, you're going to graph each inequality. And then find where they overlap. So the easiest way to do this is to denote a color for each of your lines, just so it's a little bit easier to know which one you're looking at. So my first line is y greater than x. So I don't have to do any manipulating. It's already in my mx plus b form. So I start at 0, 0 because there's no y-intercept, and I have a slope of 1. Because this is a strictly greater than, I would then do a dashed line. Now when I'm looking for my solution region here, I can't test the point 0, 0 because it is on my line. I would choose just another point on the y-axis just to make life easier. Like I'm going to test the point 0, 4. So 4 is greater than 0 would be my inequality, which is true, which means I would be shading everything above the line. For my second inequality, I do have to manipulate that a little bit before I graph it. So I have 2x plus y is less than or equal to 7. So I'm actually going to subtract 2x from both sides. So we get y is less than or equal to negative 2x plus 7. So my y-intercept is a positive 7. My slope is negative 2, so I go down to right 1. I can go up 2, left 1. I have an equal to here, which means I'm going to have a solid line. This time, I can test the point 0, 0, because 0, 0 is not on my line. So we're going to have 0 less than or equal to 0 plus 7, 0 less than or equal to 7, which is a true statement. So I'm going to shade where the point 0, 0 is, which is everything below. So when it comes to my solution region then, I'm looking to see where these inequalities overlap. So where are my red and my blue both at, which is this region right here. So any point that falls in this region that I've colored green is a solution to my system. So for example, the point negative 6, 6 is a solution. So negative 6, 6 is in my solution region. So is the point negative 6, negative 3. So there's a lot of different solutions. Any point that falls in that region is a solution. The one point that is not a solution here is the intersection point. So wherever these lines intersect, which doesn't seem to be a nice number, it looks to be at like 2.5 something. But in this case, because I have a dashed line, my intersection point is not a solution here. So next example, x minus y is less than or equal to 5, and then x greater than 4. So for my first inequality, I am going to have to manipulate it. So I'm going to subtract x from both sides. We get negative y is less than or equal to negative x plus 5. Then I have to divide everything by negative 1. So we got to remember we have to switch the inequality here because I divided by a negative. So it becomes y greater than or equal to x minus 5. So my y-intercept is going to be at negative 5. My slope is positive 1, so I go up 1 over 1. And then I can go down 1, left 1. And then it's got an equal to, which means we're going to have a solid line. When it comes to my test point, I can use the point 0, 0. So I end up with 0 greater than or equal to 0 minus 5. Which is 0 greater than or equal to negative 5, which is a true statement. So I'm going to shade everything above the line. Okay. My second inequality, x greater than 4. So that's a vertical line. So I'm going to be putting I have points that only go through my x value of 4. Oop, that's 5. Okay. This is strictly greater than, which means we have a dashed line here. And then everything greater than 4 is everything on the right side. So shade that. And then I look for my solution region where they overlap, which is in that top right part. Last example, 3y plus 2x is greater than or equal to 3, and 6y less than or equal to negative 4x minus 24. So I'm going to have to manipulate both of these inequalities. So for my first inequality, I'm going to subtract my 2x. So we get 3y greater than or equal to negative 2x plus 3. Divide everything by 3. Now, I don't have to flip my inequality here because I divided by a positive number and not a negative. So we have y greater than or equal to negative 2/3 x plus 1. So start at positive 1 negative 2/3 is down 2, right 3. And I can go up 2, left 3. This is an equal to, which means solid line. And for my test point, I'm going to use 0, 0. So we get 0 greater than or equal to 0 plus 1, which becomes 0 greater than or equal to 1, which is not true. So I'm going to shade everything where 0, 0 isn't, which is everything above the line. For my second inequality, I don't really have to do a lot to manipulate it because my y is already by itself. I just have to divide everything by 6. So when I divide everything by 6, we get y less than or equal to. I am also going to get negative 2/3 x here because negative 4 over 6 is 2/3. And then minus 6. So when it goes to graphing this inequality, I start at negative 6. I still have a slope of negative 2/3. So I'm going to go down to right 3, and then I'm going to go up to left 3. Also an equal to, so solid line as well. And then for my test point, I'm going to use the point 0, 0. So I get 0 less than or equal to negative 6, 0 minus 6, which is 0 less than or equal to negative 6, which is not true, which means I'm going to shade everything where 0, 0 isn't, which is below the line. So if I look here, there is no region where these lines overlap. So this is going to be an example of no solution. Because there is no overlap. Now, unlike with a system of equations, when we had two parallel lines, we could automatically say it's no solution. We cannot do that for a system of inequalities. Just because two lines are parallel for a system of inequalities doesn't necessarily mean that it's automatically no solution. It depends on where the shading is. It depends on what the inequality is. Because this could have easily, like if it had been y is greater than or equal to, so if I changed my inequality, then I would have shaded above the line, which means there would have been an overlap. They would have overlapped at some point. Same thing with my previous example. If it had been less than or equal to instead of greater than or equal to, they would have overlapped. So just because you have two parallel lines for a system of inequalities does not necessarily mean it is automatically no solution. You still have to graph them to see if they overlap in their solution regions. Let me know if you have any questions about graphing inequalities, a system of inequalities, or finding a solution.